So by definition, if we define, say, a function f of x is bijective if it's one-to-one and onto. Okay, so a function f of x is bijective if it's one-to-one and onto. If it is injective and surjective. So I've used two terms. So I'm saying a function f is bijective if it's injective and surjective. Injective means one-to-one. Subjective means onto. So if I illustrate, if you have a function f and some numbers 1, 2, 3, 4, 5, 6, and this goes here, this comes here, this comes here. The way it is both one-to-one and onto. If I put a number here, we'll put a different number. If I put 7 and I send it to 6, the function is onto, but not one-to-one. Because we say it's onto when all the elements in Y have got inputs coming from X. If all the elements in Y are being mapped to some elements in X, then it's onto. Okay? One-to-one, we want to see an arrow from each of the left. Then I also, before I forget, I make a comment. Please note that we do not repeat numbers on arrow diagrams. What do I mean? If I have X, 1, 2, 3, 4, being mapped to Y, 1, 2, 3, 4, and the map is F, which is 1 to 2, 1 to 3, 1 to 1, and 2 and 2, 1. Then we draw. First, we put X here. Then we put Y here. Another thing is, before you look at the relationship of F, or that is in F, you first put all the elements of X, 1, 2, 3, 4. And then put all the elements of Y, 1, 2, 3, 4. Then you start mapping now using F. 1 goes to 2, so 1 goes to 2. 1 goes to 3, so 1 goes to 3. 1 goes to 1, so 1 goes to 1. 2 goes to 1, so 2 goes to 1. You need to list 3, 4, 3, 4 in each, even if they are not being mapped to any. Then you are asked, is this a function? You say, not a function. Because 3 and 4 are not mapped. Even if they were mapped, 1 is mapped to more than one element in the Y. So it means that it's not a function. Now we get back to, okay, there's a question.
I have a question.
Okay.
Does it matter the arrangement, as in how you align the numbers?
As in starting from 1, 2, 3, 4, 1, 2, 3, 4.
1, 2, yeah. Or can you just put maybe 2, as in, does it matter how you arrange the numbers?
It doesn't matter. What matters is they must
matter.
not appear twice. Yes.
Okay.
Yeah, so it doesn't matter. What matters is they must not appear twice. I can't have. So in this case, because 1 is mapped to 3, then I have my arrow diagram that's 1, 1, 1, and then 2, 3, 4, and then the other one, 1 goes to 1, I have 1. Because 2 goes to 1, I have another 1. And then I have 2, I have 3, I have 4. Then I should now start saying 1 to 1, 1 to 2, 1 to 3, 2 to 1. This is not right, because if we ask whether it's not 1 to 1 or what, the quickest answer here will be 1 to 1, because I'm seeing only an arrow going to the other side. There's no number that has 2 arrows, because I've listed each number independently. So this is not the right way of doing things. The right way is here. I was just passing a comment there. Now let's look at Evans.
Is it possible for a one-to-one function not to be onto?
It's possible.
Oh, sorry, I meant an onto function that is not one-to-one.
Yeah, it is. Like this case. This is onto, but not onto.
This function is onto.
Yes.
Isn't it that an onto function on like every domain has an image? Isn't that what an onto function is?
Yes. No, not necessarily every domain. And onto is every element sitting in Y is an image.
Oh.
If I put a
So
number
meaning,
here, if I put 8, right?
yes.
8 is not an image, is it?
No.
So it's not on.
And then let's say 4 in that function doesn't have a domain. So does that make it still qualify as an onto function?
No.
So onto applies when the images all have a domain.
When all the elements in Y are images, an image is a number that has a domain.
Okay.
Yes.
All right, thanks.
Okay. Okay. Then, how then do you check if a function is bijective? if I'm given a function to check if it's bijective. Examples. One, determine if f is a bijective function. Given that one, a f is equal to 1 plus x over 2x minus 3. B, f of x is equal to x squared minus 4. Solution. Well, we need to check if this function is one-to-one. At the same time, we check if this function is onto. The easiest way of doing that is to check if both f and f inverse are one-to-one. So if I check if f and f inverse are one-to-one, then it means that I would have checked that f is one-to-one and f is onto. So you can easily check that f is onto by checking if the inverse is onto. Simply say, to combine the two, not the easiest way of checking if a function is bijective is by finding its inverse. So we check, because we have f, in this case, f of x is equal to 1 plus x over 2x minus 3. Then you let y be equal to 1 plus x over 2x minus 3. Okay, here, make x a subject. That's how we get the inverse. So we cross multiply. So we have 1 plus x is equal to y at 2x minus 3. And then expand 1 plus x is equal to 2xy minus 3y. We want to make x a subject, so we'll take this x the other side and this one the other side. So we have x minus 2xy is equal to negative 3y minus 1. So that we get x 1 minus 2y is equal to negative 3y minus 1. So that we say x, so we now divide by 1 minus 2y, divide by 1 minus 2y. So we now have x is equal to minus 3y minus 1 over 1 minus 2y. So f inverse of x is equal to negative 3x minus 1 over 1 minus 2x. This is a normal inverse function. There's no decision required for us to check whether this guy is one-to-one or not. Okay, the inverse exists and it exists in a normal way. So say, since f is invertible, then f is bijective. One of the simplest conclusions is this one. Because we have easily found the inverse of f, so it is bijective. If you feel it's too light, then you can say, okay, we have f of x is equal to 1 plus x over 2x minus 3, 1 plus x over 2x minus 3. We also have f inverse of x is equal to negative 3x minus 1, negative 3x minus 1 over 1 minus 2x, 1 minus 2x. Then we check if this is 1 to 1. So say f of a is equal to f of b should imply that a is equal to b if f is 1 to 1. If a function is 1 to 1, you want to start with f of a is equal to f of b and end with a is equal to b. If you fail to get there, then it is not 1 to 1. Now to find f of a, in f where there is x, you substitute a. So we have 1 plus a over 2a minus 3 is equal to get f of b, in f where there is x, you put b. So we have 1 plus b over 2b minus 3. And then you can cross multiply here. To cross multiply, we'll get 1 plus a multiplied by 2b minus 3 is equal to 1 plus b multiplied by 2a minus 3. Then expand. So we get 2b minus 3 plus 2ab minus 3a is equal to 2a minus 3 plus 2ab minus 3b. Then you cancel the like terms if there are any. Alright, so of course we hand is up. Okay, so 2ab is equal to ab. So they have same signs on both sides. So we cancel them because if they will meet, they will subtract. And then minus 3, we cancel. And then we have negative 3b this side. So take it this side where there is b and take negative 3a the other side so that we get 2b plus 3b is equal to 2a plus 3a. This is 5b is equal to 5a divided by 5 divided by 5. So get b is equal to a. So f is 1 to 1. Okay, you repeat this procedure on f inverse. So now we'll do f inverse of a is equal to f inverse of b. So we have minus 3a minus 1 over 1 minus 2a is equal to minus 3b minus 1 over 1 minus 2b. And then cross multiply, we get minus 3a minus 1 multiplied by 1 minus 2b is equal to minus 3b minus 1 multiplied by 1 minus 2a. Then we'll get minus 3a plus, I'm now expanding, 6ab minus 1 plus 2b is equal to minus 3b plus 6ab minus 1 plus 2a. Then this and this will cancel. Minus 1 and minus 1 will cancel. Then we put together right terms. So we have 2b plus 3b is equal to 2a plus 3a, giving us 5b is equal to 5a. Divide by 5, then we get b is equal to a. So F inverse is 1-to-1, implying that F is onto. And so, therefore, F is bijective because it's both 1-to-1 and onto. Grace? Grace, what's your question? I can see it for Grace. Edwin?
So,
Uh-huh.
so some functions don't have an inverse.
Yeah, some functions have a complicated inverse.
Then those they're not bijective.
Those are not bijective.
Now, how can you tell?
Okay, let's do B. Then we'll be able to tell. On the other hand, Mrs. I can't pronounce your surname.
Okay, like on that part for checking if a function is 1-to-1, right?
Yes.
Do you check for both the real function and the inverse, or you choose any?
No. To check if it's 1-to-1. If it was just to check if it's 1-to-1, you do the original function. But because we want to use this 1-to-1 thing to determine if it's bijective, we do it for both the original function and the inverse. When we are checking for the inverse, we want to check if the original function is
Okay,
onto.
thank you.
So how do we have functions that are not okay, Grace? Yes.
Yes, I was saying which normal way, or can you tell us the shortcut way where we can just like look at the function and know it's bijective without without going through all this? Is
You
there a
just-
way?
Just getting the inverse. If you can peacefully get the inverse, then you know it's bijective.
All right.
Yes. Okay, Precious, followed by Moma. Okay, Moma, Precious, are you grown?
So I've got the question on the second way in which you solved it for A and B. So if the
Yes.
original function is 1-to-1 and the inverse is also 1-to-1, meaning that the function is onto.
The function is onto if the inverse is 1-to-1.
Okay, the inverse is 1-to-1,
Yes.
which means that the function is also bijective.
The function is bijective if both the original function and the inverse are 1-to-1.
Okay, thank you very much.
Okay. So running out of time, let's try to solve B and see what we get. Precious. Okay, so B,
When you want to check, if you want to check the function, if it is
okay, so B, f of x is equal to x squared minus 4. We want to check if this function is onto. I mean, if this function is bijective. Wow. You can just simply check if it's one-to-one. Or you can check if it's invertible. To check if it's invertible, well, we let y be equal to x squared minus 4. And then make x the subject. Then we'll have y plus 4 is equal to x squared. If we square root, we end up having x is equal to plus or minus the root of y plus 4. Meaning that the inverse is plus or minus the root of x plus 4. The inverse is giving us two options. It is either this or the other. So we don't know which one is the inverse. We cannot say this function is invertible because we don't have its inverse. Okay. Another way is you say, okay, because I know that for a function to be bijective, it must be one-to-one and onto. Let me check if this function is one-to-one. F of A is f of B. We'll have a squared minus 4 is equal to b squared minus 4. The 4's will cancel, and I'll have a squared is equal to b squared. This means A is equal to plus or minus B. So F is not one-to-one. Hence, not bijective. Because it must be one-to-one. Then it must be on for it to be bijective. Precious?
Sir, there where a is squared and b is squared, do you square both sides?
You square root both sides, yes.
Won't they be equal?
No. If we have x squared is equal to 2 squared, this is the same thing as x squared is equal to 4. When you square root, we get x is equal to plus or minus 2. Meaning we square rooted this square here.
Okay. Let's see. Thank you.
Okay. Evans?
So you said, okay, the only way we can prove that a function is onto, is it by testing if the inverse is one or there's another one?
The easiest one is by testing if the inverse is one-to-one.
Okay.
Or simply
What's
getting
the
a
other?
normal. The other way is by getting the normal inverse. If you can get the normal inverse, then even if you don't
What do you
test if
mean
it's
by-
one-to-one, if you can
What do you mean by
obtain the
normal
inverse that is well decided, look at this inverse here. We have an inverse here.
Okay.
This one is not a normal inverse
Oh, okay.
because it's plus or minus, so we don't know which one is which.
Okay, thank you.
Okay. Muma.
Also, my question was, since here it's x squared minus 4, so in a case where it is cube root, does it mean that this one becomes 1-to-1? Because in some research, I found that when it was a cube and b cube, it was 1-to-1. So I wanted to confirm with you.
Yes, it will be.
Oh, okay, thank you.
Yeah, because the cube root has got a special behavior of giving only one value.
Oh, okay, all right. Thank you.
Mono.
Sir,
Sir,
on this,
kindly on
when
the
finding
first one,
the,
Okay, let's start with mono. Yes.
this part that we're dealing with is finding the bijective, is it something? Yeah.
It's checking if it's
Then what?
bijective.
Yeah, those situations where you're asked to find if it's 1-to, to decide if it's 1-to.
If it's 1-to-1.
1-to or 1.
Uh-huh.
Are we supposed to use this formula for A is equals to B, or maybe we can still use the issue of finding the inverse?
No, there when you're asked to check if it's 1-to-1, you use A, f of A is equal to f of B.
Okay.
If it's onto, then you get the inverse and check if it's 1-to-1.
Then if it's both, we use this one that we're using now.
Then if it's
We
both,
do it like this.
then you do it like this because you're checking if it's bijective now.
Okay.
Monica, what are you saying?
sir, I was logged out. I didn't get on that one where you're saying if it's not a normal inverse, something like that. I didn't get. Can't really repeat.
So we are saying in the case where you have an inverse that is giving you two options, we call this not a normal inverse. So I'm saying it's not a normal inverse because it's giving me two options. It's saying my inverse is either the root of x plus 4 or negative the root of x plus 4. So I don't know which inverse to use. I'll be using the inverse given conditions. So I'm saying it's not a normal inverse. The normal inverse is the inverse that when you get it, I mean, there's nothing else to be said. F inverse is equal to negative 3x minus 1 over 1 minus 2x, full stop. No further explanation. If you find yourself explaining how it's an inverse, then you know it's not a normal inverse. It's an inverse given conditions. Clifford.
Okay, sir. Thank you.
Okay.
So it's actually okay. I wanted I was kindly asking for the previous slide where you talked about the onto function, but it's okay.
Okay. Good. So it's just that time has run out. We're supposed to now check if a function fails to be bijective, like in this case, are we able to make it bijective? That's where we're starting from tomorrow. Tomorrow we'll check when it fails to be bijective, what do you do to make it bijective? And then from there, we'll now start sketching. So we'll also use the sketch way to determine if the function is bijective or not. Edwin, you have seconds.
Can I ask a question on polynomials?
So you ask tomorrow because now we just have seconds.
All right. Thank you.
Yeah. So I hope to have you all tomorrow. Have a good night.
Thank you, sir.
Oh, you